Hey guys. Saying hey guys feels kind of fucking stupid. Like I'm Dora the Explorer. Like, hey guys, want to talk about ligand receptor interactions today? Great, let's get into it. So I figured I've been covering more uh, niche topics so far. That is, in my videos, I've talked about NMDA receptors. I've talked about gabapentinoids and GABA receptors, but I'd like to kind of take a step back here, take it back to the basics. Ligand receptor interactions. Just an overview of how different ligands interact with receptors. That includes agonists, antagonists, and allosteric modulators. So first off, just to establish what a ligand is, in biochemistry or pharmacology, a ligand is a molecule. It can be a diverse range of different types of molecules. There are amino acids, there are various drugs and xenobiotics, and within the body you have hormones and I already said amino acids, but there are essentially lots of different types of ligands, but generally they can be categorized into these three groups. So what a ligand does is it associates with the receptor. Right here I just drew a unnamed receptor. It looks to be ionotropic, but that's irrelevant here. So a ligand binds to a site on a receptor, and a site is essentially just a location on the receptor that's conducive to interaction via either intermolecular forces like ionic bonding, van der Waals forces, or less commonly through covalent bonding, which is irreversible. But receptors generally have multiple binding sites. There's generally an orthosteric site, or multiple ones in certain cases, where the endogenous ligand of that receptor binds to. And just to go over endogenous versus exogenous, endogenous means that the ligand in question is naturally occurring within the body. Exogenous means occurring from outside of the body, like a medication or drug or other substance that can elicit effects. So yeah, generally the orthosteric site is the common site that the endogenous ligand binds to. Like in the case of the GABA receptors, it would be the orthosteric site would be the site where GABA binds. With NMDA receptors, there would be two sites where glycine and glutamate would bind. There's also the allosteric site, which is a regulatory site. It, when bound to, it either positively or negatively modulates the efficacy, that is the strength of the biological response that the receptor propagates, or it affects the affinity of other ligands to the orthosteric site generally. It can either do one or the other, or it can do both, but it does not bind to the active site, the site that agonists and most antagonists bind to. For illustrative purposes, I've drawn this as a side view, where this is the membrane, the cellular phospholipid bilayer membrane. This would be extracellular space outside of the neuron. This would be intracellular space inside of the neuron. And receptors are generally comprised of multiple subunits. In the side view, it's very simplified. It looks like it's just like two units and like a pore through which ions can travel. But in reality, receptors are often complexes of multiple subunits. There are pentameric complexes, meaning they contain 5, like the GABA receptors, and other conformations of subunits. So this is really just a simplified illustration for explanatory purposes. Now, let's get into what different types of ligands there are. So I'm going to start off with the agonists. Now, an agonist is a ligand that binds to the active site on a receptor, the orthosteric site, and it activates the receptor, as in it induces the transduction of a signal. The signal can be in different forms. Like in the case of an ionotropic receptor, it might be the opening of an ion pore or a channel pore in which ions will flow into the cell and cause the biological response. Or it could be G protein coupled, where there is the use of a secondary messenger intracellularly, where the agonist binds to the site, and that causes a conformational change. And when it changes, it causes something to happen within the cell. In the case of a neuron, it might stimulate the release of a substance. It might recruit a molecule, but generally it results in the recruitment of a secondary messenger. And that secondary messenger then might trigger a cascade, like a pathway of signal transduction through other messengers, or whatever it may be. So there's different traits that agonists can possess, and those are reversible or irreversible. Now, an agonist can be reversible in the sense that it does not bind covalently, and most agonists are reversible. Irreversible agonists are much less common than reversible ones. Reversible agonists bind using either an ionic or an otherwise intermolecular force, like a van der Waals force or hydrogen bonding or something like that, like a weak force. So they're able to disassociate from that receptor eventually. They can either be selective or non-selective. Selectivity references whether the agonist is preferential for a certain either type or subtype of receptor. For example, SSRIs, selective serotonin reuptake inhibitors, are fairly selective at inhibiting the serotonin transporter protein. Well, in that case, that's an example of a selective antagonist. But yeah, they can be selective or non-selective. If they're non-selective, they have a more diverse, or dirty is a colloquial term used, binding profile. And a binding profile is the targets that a ligand has affinity for. Now, affinity is the ability for a ligand to bind to a receptor. On the other hand, efficacy is the degree of biological response triggered by that ligand binding to something. So then we have biased and unbiased agonism. Biased refers to the method of signaling. Often in different types of receptors, there might be different mechanisms of intracellular signaling that can occur depending on the ligand type and depending on the site that it binds to. One that comes to mind is CAMP signaling versus beta-arrestin signaling, CAMP meaning cyclic adenosine monophosphate versus beta-arrestin. So there's not always just one secondary messenger. It depends on the receptor. It depends on which site is being activated and how that changes the receptor, and how that change results in the propagation of the signal transduction through a secondary messenger. And then there's exogenous versus endogenous, which I already went over. So those traits apply to all of these here. The general receptor phenotypes. We have full agonists, which elicit the full maximal biological response. Then we have partial agonists, which, as the name implies, they have partial efficacy. They don't elicit a full response, that is, the full possible biological response that could be elicited through that receptor. And then we have inverse agonists, which, interestingly enough, they bind to the active site and they elicit the opposite response that a typical agonist would. So in that sense, they're sometimes also grouped in with antagonists, because they might prevent full or partial agonists from binding to a site, and then they inhibit the activity of that receptor. In terms of antagonists, the traits that they can exhibit are reversibility or irreversibility, same as agonists, selectivity or non-selectivity, and endogenous or exogenous occurrence. Those are all shared traits with agonists. The only one that the antagonists don't share with agonists are biased or unbiased, because by definition, an antagonist has zero efficacy at a receptor. That is, when it binds to the receptor, it does not activate it. So it has, by definition, zero efficacy at the receptor. So the three main types of antagonists are competitive antagonists, named as such because they bind to the same site as the endogenous ligand, the orthosteric site. So they bind to the orthosteric site and prevent an agonist from binding to that site. So they reduce the activity of the receptor by blocking agonists from binding. And at high enough concentrations, they can also displace agonists that are already bound to the receptor. They're called competitive in that sense because they compete for the site on the receptor. Then we have non-competitive antagonists. These ones bind to an allosteric site, like illustrated on this here. While a competitive antagonist would bind to the same site as the endogenous agonist, a non-competitive antagonist would bind to a different site. So the agonist can still bind, but the antagonist here, in this case, reduces the response, that reduces the efficacy of the agonist at that receptor. So then the third category is uncompetitive antagonists. An uncompetitive antagonist requires receptor activation by an agonist before it can bind to an allosteric site. So it's similar to a non-competitive antagonist, but it requires the condition that an agonist is already present at the orthosteric site. So then I also included partial agonists and inverse agonists under the category of antagonists, because in certain situations they can act in a similar way to antagonists. That is, for example, a partial agonist. If you have partial agonists and full agonists both competing for sites, the partial agonist will prevent a full agonist from binding, and it'll still trigger or activate the receptor. It does so with lesser efficacy. So it can act as a pseudo-antagonist in that sense that it can dampen the effects of a full agonist when they're competing for a site. Now, inverse agonists also are somewhat pseudo-antagonist in nature because they can compete for, just like partial agonists, they can compete for the site that a full agonist might bind to and prevent the full agonist from eliciting the full maximal biological response. But also they induce the opposite effect of what that full agonist would do. So in that sense, it's the polar opposite of a full agonist. Then we have allosteric modulators. So an allosteric modulator is a ligand that binds to the allosteric site on a receptor. That is the regulatory site, the modulatory site. And there are three types. There are positive allosteric modulators, or PAMs, which bind to the allosteric site and either increase the affinity or the efficacy or both of the orthosteric ligand. Then the negative allosteric modulators, or NAMs, do the opposite of that. They bind to the allosteric site and they either reduce the affinity or efficacy of the orthosteric ligand. Neutral allosteric modulators are a bit less common here. They are an allosteric modulator that binds the allosteric site but doesn't do anything. It doesn't modulate the orthosteric site, or it doesn't modulate the receptor. What this means is it's almost like an allosteric antagonist, in the sense that it's blocking other allosteric modulators from binding to that allosteric site. So it binds there and blocks the activity of other potential positive or negative allosteric modulators from binding there and regulating the receptor. An example of a positive allosteric modulator would be a benzodiazepine. They bind to the allosteric site on the GABA receptor, and they increase the activity of those receptors by modulating the efficacy and affinity of the endogenous neurotransmitter GABA. That about covers the most common and important, I guess, ligands, at least in terms of pharmacology. I just decided to make this kind of shorter, more basic video on ligand receptor interactions because I'm currently running a SOXLIT extraction, which will be shown in another video, and I have time to kill while I'm babysitting that. So yeah, if you're already into pharmacology, I'm sure a lot of this you might already know, and hopefully this is kind of a good refresher or top-down overview. And if you're not into pharmacology or you're interested in it and interested in learning, I hope that this video might provide a simplified explanation of this incredibly important topic. Ligand receptor interactions are pervasive in pharmacology. It's important to learn the general different types of ligands and how they interact with receptors before you really delve deeper into the ways that specific ligands interact with specific receptors, because then you have more of a baseline knowledge of how it works and how it could work with different substances. But anyways, I think I'm going to do more videos on pharmacology basics because while I do enjoy spurging out about specific facets of pharmacology, I think that talking more about the basics, hopefully in a way that is understandable. Yeah, anyways, thanks for watching.